We have our second speaker of the evening, who has got my bathroom cabinet lined up as his screensaver. But yeah, Alex, are you ready? And shall we hand over to you for your talk, please?
Yeah. Let me just, the magic of screen sharing, let's see if it all works. Excellent. Well, thanks and good evening, everyone. I'm an organic chemist at the University of Warwick, and as an organic chemist, I spend most of my time making new molecules from carbon building blocks. And what really fascinates me is how we can make very small changes to these molecules, such as just one carbon, and it can have a dramatic change on how that molecule behaves. And this is especially true for medicines. So today, I want to talk about that thin chemical line that separates medicines from illicit drugs. Now, a quick point about chemical structures before I go any further. In chemistry lessons at school, you may have seen the structures on the left, where we show every atom, and we give every atom its elemental symbol from the periodic table, and every line is a bond. Now, when we get to university, we remove all the carbons and the hydrogens bound to those carbons from our structures, because it's just so much easier to read and draw. Now, by doing this, well, we do this because carbon and hydrogen are actually incredibly in common in organic chemistry. And what we're left with are these skeletal structures where every connection is a carbon with the right number of hydrogens attached to it. So to start with then, let's have a look at these two chemicals. These molecules aren't groundbreaking in any way, but when you give them a small amount of oxygen by shaking them, they will change color. Now, the addition of oxygen to the reaction allows the molecules to rearrange their structures and shift their hydrogens and electrons around. Now, eventually they will go back to being clear and colorless as they rearrange their hydrogens and electrons again back to their starting positions. Now, as I said, these molecules are not world-changing, they're not groundbreaking, but they do illustrate a very good point that a very small chemical change of only a few hydrogens can have really dramatic consequences on how a chemical behaves. Yeah. So this is really the point of my talk today, to show you that simple chemical changes change the world, and that when these changes are made to medicines, well, the effects can be disastrous. Medicines go from chemicals that heal us to chemicals that harm us. Now, I'm going to illustrate this today by answering two big questions. The first, why is heroin so addictive? And the second, why is half of all methamphetamine inactive? To answer the first, then we actually have to go back to ancient times, to the Sumerian civilization, who lived over 5,000 years ago in present-day Iraq. Now, the people in this region were cultivating a plant they called whole gill, or the joy plant. We know it today as the opium poppy. Now, the juices of this poppy they would use in anything from anesthetics for quite major surgery to benign headache cures. Now, the use of the poppy would then spread across the ancient world to Greece and Egypt, where it would actually be worshipped as a god. And then it would spread further into China. And actually in 1527, it would then be rediscovered in Europe by the alchemist Paracelsus. Now, it wasn't actually until 1804 that the active ingredient of the poppy was understood, morphine, and that was isolated by a chemist called Saturna. Now, during this period, the popularity of opium and morphine as drugs was really starting to take off globally. In China, the problem of opium was so bad that the Chinese government wanted to stop opium imports into China altogether. Now, this is really unsurprising because when you look back at the data, China in 1 year in the 1850s was importing 10 times the global amount we now produce yearly. However, as with most things in this period, the British Empire disagreed and they got their way. So they forced China at gunpoint to take the opium. This was drug dealing on a colossal scale, but from a British perspective, it did lead to the ceding of Hong Kong to the UK in 1842. Now, To take opium or morphine in this period, you would often smoke it or take it orally. And it wasn't actually until 1844 that the first hypodermic needle injection of morphine was carried out. Now, this was really important because it solved the problem of accidentally overdosing your patient when you give them opium or morphine orally. Now, this brings us to the current use of morphine in the NHS, where it is used as a potent painkiller for heart attacks, post-surgery pain relief, and palliative care. But how does it work? Well, when you experience pain, this is because your nerve impulses are traveling along your neurons to the brain across nerve junctions, and they're carried across those nerve junctions by chemical neurotransmitters. Now, when you take morphine, it enters your brain, binds to opioid receptors on the junctions of those neurons, and this prevents the neurotransmitters from being released. This literally stops nerve impulses in your brain, so you don't feel pain. Which sounds very good, but really, the issue with morphine and other opioids is that over time, your body starts to adapt to the morphine, and you don't get the same pain-killing effect you got previously. It starts to dampen. This means you need to take more and more morphine to get the same response. And this leads to dependence and addiction. So for many centuries, the holy grail of addiction-free morphine has been the pursuit of doctors and researchers. Now, one such researcher was an Englishman called Charles Alderwright. Now, in 1874, Alderwright was attempting to make this holy grail addiction-free morphine. And he was doing this by reacting pure acetic acid, a key ingredient in vinegar, with morphine. And he successfully made a chemical that he called diacetyl morphine by adding these two acetyl groups I've put in red boxes. He then took his new chemical, and because ethics was particularly weak at the time, he just started testing it on small animals. And he realized pretty quickly it had a very similar effect to morphine. So he didn't actually take this work any further. However, Alderwright's work was actually picked up in sort of the late 1890s by a German chemical company who were also trying to make addiction-free morphine. Now, they carried out the same reaction as Alderwright and realized his chemical is a very good painkiller. But, you've got to sell the chemical. Diacetyl morphine is not a great name, so we want something more catchy. So they called it heroin, because one of the other side effects of heroin is it makes you feel invincible like a hero. So they then took their new drug and they marketed it as a cure for toothache and headache alongside their other invention, aspirin. Now, this company is now called Bayer, and it's worth $100 billion US. Now, at the time, in fairness to them, they thought heroin was a non-addictive solution to morphine. Of course, we now know that is not the case, and it's actually highly addictive. So in the UK, it is a Class A drug. So coming back to the main question then, why is heroin so addictive when the only difference between our heroin molecule and our morphine molecule are these two acetyl groups? Well, there was an experiment carried out in 1972, and it was carried out on rats. The experiment was set up to look at how easily opioids, morphine and heroin moved across the blood-brain barrier. Now, this is a very thin layer that separates your blood from your brain tissue. In this experiment, they took the rats and they injected some of them with morphine. Then after 15 seconds, they decapitated the rats and looked at the amount of morphine on either side of the blood-brain barrier. And it was found after 15 seconds that no morphine had gone from the blood into the brain of the rat. They then repeated their experiment and dosed the rats with heroin. These are, of course, new rats, not the decapitated ones. And after about 15 seconds, they realized that 63% of the heroin they put in the rat's blood was now in the rat's brain. And it turns out that heroin is far more soluble inside the fat of the blood-brain barrier and brain than morphine is. This means it moves across the blood-brain barrier far more effectively than morphine. To illustrate this, what I have here are two solids in liquids they aren't soluble in. You can see you've still got particles. However, when I now add liquids they are soluble in, you'll see how quickly they move into those soluble layers. And in fact, in a minute, I'm going to spin them even faster to try and drive the chemicals back into the insoluble layers. And you'll find that just doesn't happen. You can't drive them back into the insoluble layer. Now, this is important because for something to be chemically active, it has to be able to reach its target. If it has to go through a solvent or a layer it's not soluble in, it won't work. It simply won't reach the target. Think of it like this. A T-Rex is a land-based predator. It can only hunt on the land. If you stick a T-Rex in the sea, you'll quickly realize that the T-Rex no longer functions as normal, and the T-Rex will try and get out of the water at all costs. Now, in this way, and to a first approximation, heroin is like a T-Rex. Both are poorly water soluble. Both prefer non-water-based environments. Now consider as a thought experiment, dropping a T-Rex just off the coast. It will quickly swim to the shore, and now that it's back on land, it'll start being active again. This is just like heroin in your blood. Heroin moves out of your watery blood into the nice fatty environment of the blood-brain barrier, and then into fatty brain tissue. Now, when heroin is actually inside the fatty environment of the brain, something quite interesting happens, because the majority of heroin molecules are actually broken down within about 10 minutes to monoacetylated morphine. That's morphine carrying one acetyl group. And then within about 30 minutes to morphine. So both morphine and monoacetylated morphine are the actual active ingredients. They carry out the function. This means that for heroin to have any effect in your brain, it actually has to be broken down into morphine and monoacetylated morphine. So in this way, heroin is actually what's known as a prodrug. It has no activity itself until it's broken down into its active morphine forms. So why is heroin so addictive? Well, a simple chemical change adds two acetyl groups. This massively increases its solubility in the brain and the blood-brain barrier. So it is driven across the blood-brain barrier far more effectively than morphine is. Once it's in your brain, it's then simply broken back down to morphine. So heroin is in fact a great way to transport morphine more effectively into the brain. This is why heroin is so addictive. It's simply more soluble in your brain than morphine, so more of it gets there. Now, this very simple chemical addition of two acetyl groups costs the US about $50 billion a year, despite only 0.2% of its population using heroin. So this simple chemical change of adding what is basically concentrated vinegar to morphine has truly changed the world. And I think that is some food for thought when you're next down the chippy and you're putting vinegar on your chips. Question 2 then, why is half of all methamphetamine inactive? Well, N-dimethylphenethylamine is a medicine used in the US as a nasal decongestant. Interestingly though, this medicine is what's known as an enantiomer. It is a molecule that has a non-overlapping mirror image of itself. Now, if you take both your hands and hold them out in front of you with palms facing away from you, they are mirror images of each other, but they don't overlap. Your thumbs will never be on the same side unless you turn one hand over. Now, in this way, your hands are like enantiomers. Now, what I've done here is highlight this wedge bond, because on chemical structures, a wedge bond shows a bond coming out of the screen and indicates that these two structures are actually enantiomers of each other at that position. Now, I'd mark that in red so it's more easy to see. Now, enantiomers are found in lots of places. For example, here are two enantiomers, both of limonene. The left-hand one has a bond going into the screen and gives lemons their smell, so it's added to food and perfume. The right-hand one has a bond coming out of the screen and smells like turpentine or petrol. So unsurprisingly, it's not added to perfumes. Now, this is a very simple chemical difference that will cost a perfumer their job, and possibly you and Night on the sofa if you turn up with Chanel No. 5 and it smells of petrol. The only difference is one bond facing either up or down. Here's another pair of enantiomers, this time of a chemical called carvone, a chemical you'll notice only a few hydrogens different and an oxygen different from limonene. Now, the left enantiomer gives caraway seeds their smell, and the right gives spearmint its taste and smell. Again, the difference of a bond going up or down changes their smell, taste, and use. So in the cases of limonene and carvone, a very simple chemical change dramatically affects how your body reacts and smells the chemicals. Now, in medicine, enantiomers can be a truly huge problem. The enantiomer of our nasal decongestant is methamphetamine, commonly known as meth. Now, meth is a drug that causes euphoria, increased self-confidence, and reduced fatigue because it leads to massive dopamine release. Now, the issue with these two enantiomers of methamphetamine is it's difficult to make one of them without ever making the other. So whenever you synthesize the medicine, you also get the drug. And the only way you can separate them is after you've made them. So this is why half of all methamphetamine is inactive as a drug, because the other half is a nasal decongestant. Now, whilst this probably doesn't mean a drug dealer will give you a 50% discount, it does highlight an interesting quirk of chemistry, that even molecules that contain the same atoms in the same places can have very different reactions and effects on the body. Now, to separate the drug from the medicine, you actually have to run them through what's known as a chromatography column. And this allows you to separate your two enantiomers based on their solubility. For example, if A is more soluble than B, A will come through your column much faster. Therefore, we collect A before B even leaves the column. Now, this allows us to separate our enantiomers. However, this technique is incredibly difficult to do on a large scale, and it's time consuming and requires lots of skill. So unsurprisingly, a drug dealer won't do that. So half of all methamphetamine is inactive for two reasons then. One, the reaction to synthesize meth produces two enantiomers. And two, you can only separate the enantiomers by using a column, which is slow and expensive. Now, that's not quite where the story ends though, because that's not the only way you could make methamphetamine. And this brings us to another giant, an unfortunate giant of drug chemistry, a Japanese scientist called Nagai Nagayoshi. Now, in the 19th century, Nagai Nagayoshi, who interestingly is actually only a month older than Alder Wright, the person who synthesized heroin, well, Nagayoshi was studying ephedrine, a chemical found in this plant here, Ephedra distachya, a common weed that's used in Chinese medicine as an anti-asthmatic. Now, perhaps more interesting and what Nagai would like to be remembered for is that ephedrine is actually very chemically similar to epinephrine, or as we call it in the UK, adrenaline. Now, this chemical was first isolated in its pure form by one of Nagayoshi's students, Kiezo Uenaka. So as you can see, Nagayoshi has a pretty vast scientific legacy, but probably his most infamous discovery happened in 1893 when he worked out how to take ephedrine and convert it to methamphetamine in what is called the Nagai method. Now, fortunately, this reaction step is not particularly high yielding, because if you take this weed and try and extract ephedrine from it, only 3% of it is actually ephedrine. So it's not a fantastic source for drug synthesis. However, unfortunately for Nagai, his method works on all forms of ephedrine, including what are known as pseudoephedrine. Now, these are isomers of ephedrine. Pseudoephedrine is a medicine that you find in cough syrup, which, if you've ever wondered why drug dealers buy lots of cough syrup, that's because it contains pseudoephedrine, and they will then use that to make methamphetamine. And this is the method they actually use in the TV show Breaking Bad. Now, crucially, the only enantiomer of pseudoephedrine found in Sudafed and other cough medicines is the one used to make methamphetamine. So you've already got this pure substance that you can now take straight to the drug, and you no longer have to worry about making the medicine on the side if you're an illicit drug dealer. Fortunately, however, the cost of cough syrup has always controlled the availability of methamphetamine, because cough syrup is quite expensive and often rigorously controlled by governments. However, more recently and more worryingly, what you might have seen in the news are drug producers in Afghanistan rediscovering the use of ephedra plants like Nagayoshi realized. And you can use those ephedra plants, which are common in Afghanistan, to isolate ephedrine on a truly large scale. And again, unfortunately for society, the naturally occurring and most abundant enantiomer of ephedrine is the one you find naturally occurring in the plants. And that's the one that when you put through the Nagai process, gives you the drug methamphetamine. And this means that in Afghanistan, you can take this weed for about 74 US cents, and you can turn it into crystal meth that's worth 305 US dollars a kilo before you even consider exporting it. And it's thought that this rediscovery of a reliable ephedrine source in Afghanistan will dramatically affect drug abuse and drug use around the world. So why is half of all methamphetamine inactive? Well, honestly, it depends how you make it. And seemingly the methods used by drug manufacturers really vary by the availability of the chemicals and the skill of the producer. So let me quickly finish by looking at whether drugs can go back to being medicines. So in the case of methamphetamine, as we've already seen, a derivative of it is found in Sudafed. And actually, interestingly, some of the side effects of Sudafed, if you read the packet, will say hallucinations like methamphetamine. While the addictiveness of heroin and morphine have necessitated the need for an opioid-free synthesis of codeine, so a way to make this painkiller codeine without going anywhere near opioids. Plus, an enantiomer of heroin is actually found in night nurse. Well, a derivative of an enantiomer of heroin is actually found in night nurse. So some drugs can go back to being medicines as well. In summary, then, we've seen why heroin is so addictive and why some forms of methamphetamine are inactive. And in both cases, it comes down to very simple chemical changes that have had huge world consequences. Thanks for listening.
Thank you, Alex. That was great. Evie, I think I've seen a couple of questions come up in the chat for Alex.
We do have some questions. Keep them coming. First question is, how does methadone fit into this picture?
Let me just quickly Google the structure of methadone. So I think it's more, yeah, okay. So methadone, when you have the structure of methamphetamine, you notice there's that nitrogen group at the end. So in methadone, you keep that piece there, and you're just changing some of the other groups in the molecule. So as we saw with heroin and morphine, by adding a few different groups, you can change solubility, you can change what you target. So with methadone, it is chemically quite similar to ecstasy and methamphetamine, but by changing and tweaking these groups, you can slightly change the way that someone could take it. You can change the target sites you want to go for. So they're chemically quite similar, but by making these slight tweaks, you can slightly change how the body reacts to them.
The next question is, has there ever been a successful attempt to make a non-addictive version of a drug?
So paracetamol is actually quite a good example of a drug that is not chemically addictive. So, and to be honest, our understanding of why is not particularly well fleshed out. But yeah, there are some drugs which aren't chemically addictive, so your body doesn't have a physiological change. So with something like morphine, these opioid receptors, your body just stops showing as many opioid receptors, or sometimes shows more depending on what you're doing with it. But paracetamol is more of a psychological addiction, it would seem, is my understanding of it at least.
Is there a way to distinguish which one is more difficult to overcome? Is it psychological or physical, or is that not comparable?
I don't know. I mean, it depends on the power of the mind. So, and also how dramatic you see these physiological changes being. So we know that with medicines like ibuprofen and some other things like aspirin that work through certain routes. So aspirin hits two enzymes to give it physiological activity. Now, we know that hitting one of those enzymes, one of those protein, leads to quite negative effects, which is why we don't really like prescribing aspirin for really long-term conditions at high doses. But by slightly changing the chemical structure, we can just hit the one enzyme and protein we want. So arguably, the chemical addiction is easier to overcome if you never become addicted, because hopefully at the kind of the making it and synthesizing, coming up with the drug structure stage, we can take those problems out. So it's kind of I don't know if there's a difference between how strong the chemical and the psychological addiction would be, but the chemical one we can at least try and overcome by doing better chemistry. From my perspective as a chemist, that would be what I would try to do.
Next question is, does the chemistry inform what is made illegal?
So there was recently, we got into some quite questionable areas with this, actually, with, I believe it was a policy that when Theresa May was Prime Minister, she tried to bring in, where she just wanted to say things that look similar or have psychoactive effects, well, we're just going to ban them outright. Actually, you can't do that, because tiny changes can have really quite big problems. There was a pharmaceutical company, I believe in India, that were looking at patents around drugs. Now, when you patent a drug, you give its chemical structure. And they were looking at ways to get around this. So what they decided to do was just throw on what they thought would be an inactive addition to their chemical structure, hoping that, well, it would still react in the same way, surely. This wasn't the case. And they ran into serious problems very quickly. So whilst we can try and predict activity based on structure, and to a certain extent it follows, the human body is so complex that sometimes these small changes can start targeting other parts of the body that we really don't fully understand. So to an extent, yes, but it would be a very brave chemist to just go, this is safe because it looks similar to this, or this has the same function because it looks similar to this. We always have to go back and do full and thorough testing.
Next question has sparked some back and forth in the WhatsApp group, so we need you to judge. That is, as an ex-smoker, when I was giving up, I was told that nicotine was more addictive than heroin. Is there an inactive form of nicotine similar to opium and heroin and meth and nasal decongestions?
So, firstly, it depends how we're going to judge addictiveness, and comes back to the chemical versus psychological addictiveness. So, the argument of alcohol is a more dangerous drug than, these strong opioids because it has a greater societal effect. So it really depends how we're going to measure that addiction. So if we look at something like nicotine, it is highly addictive, but really you've got to go back and look at those papers. Are they judging that on a big societal level of there are more smokers of tobacco than heroin or morphine or methamphetamine, all these other things? So it really depends how you're going to start measuring them, because you've got chemical addictiveness, psychological addictiveness we've talked about, but then also societal impacts. Because there are lots of major drugs out there. Actually, their societal impacts aren't as bad as some much more common ones. So actually targeting those drugs and trying to take them out of the system would be far better. But whether there's the political will to say, let's just ban smoking, let's ban drinking, because these are dangerous chemicals and have huge societal impacts, whether anyone would ever buy into that is, difficult to judge. And that's where society and politics play their role in chemistry.
Next question is, are there any everyday foods which I'm eating which might be affecting my brain without realizing?
So the simple answer is probably yes. But the argument would be, so if you looked at something like potatoes, we know that in the skin of potatoes you find chemicals that are very similar to nightshade, the poison, but there's such a low concentration in there, it's never really dangerous for you to eat. But we also know that if you eat too many bananas, you massively raise your potassium levels, and that can also lead to serious problems. So, it's a bit like what the vicar says in Romeo and Juliet about, medicines are medicines until you start having massive amounts of them. The same with certain foods. If you eat them in moderation, and we're talking, you'd have to massively eat them beyond moderation and eat them just as your soul diet, and really just eat through bananas all day, every day, and that was your only thing, then you might start to see problems. But, safely, no, not really.
Intriguing question is, what do the companies, the manufacturers, do with the half of their production that cannot be used as medicine?
So sometimes you can take it, then drive it back the other way. What is becoming more common, and why I said that the enantiomer of methamphetamine, the medicine, is only actually sold in the States, is because lots of other countries have said, well, what's the point in making something like this when actually by simply changing a few more groups, we can make a perfectly safe medicine that doesn't take us near making the drug, which is where codeine comes into play. Because the good thing about codeine is we've worked out a way to get all the way to making codeine without having to go anywhere near chemicals that have these opioid effects. So by taking any potentially dangerous drugs out of our synthesis, or dangerous reagents out of our synthesis, we can often avoid these problems. So sometimes the best solution is simply to say, well, we're not going to make that anymore. We're just going to find a better chemical to fill its place, where we're not going to have this problem.
Right. Last question. There's a couple more in the WhatsApp group. You might want to answer them during the break or later. But the last question for now is, why is it that some drugs will affect some animals and not others? Or why does catnip not affect me?
So I'll take it from another direction and talk about my actual research is more around COVID. And if you look at something like COVID only affects certain species, because in humans and bats and pigs, we have certain receptors that cats, dogs, and other mammals don't have, which is why some foods and some medicines and things like catnip have far bigger effects on certain animals, either because they have more receptors for these foods and medicines, or because they simply have receptors that we don't have. So really, it's a big mix. But then you've also got the argument of, well, a cat is much smaller than you, so it takes a lot less medication to have the same effect. So there are all these other sort of pharmacy arguments that you need to have as well about dosing.
Excellent. Thank you very much. I hope that the minks that keep getting COVID have some fun receptors for some fun drugs, because they have been punished very badly this pandemic. Thank you very much. Over to you, Louise.
Thank you, Evie. And thank you, Alex. You did a really good job there of explaining very clearly some interesting concepts. It's possibly the first time I've ever managed to follow a presentation that involved chemical diagrams. So I appreciate it.